Well, good morning, everyone. For the little batch of you that are here, I'm Jason Hoffman. I'm founder and chief scientist of a company called Joyent, and I'm going to talk to you this morning about a little thing where, well, some people call it the Internet of Things. I mean, the other way of thinking about it is that the world's basically the next big computer. And so when we take that sort of idea, then we really have that we're heading towards this trend where very much the network has become the backplane. And we've been moving from things like client-server to really synced real-time peers. The data center happens to be one peer with billions of devices surrounding it. When we begin to actually start looking at the size of just sort of general data growth, we can get some indication of some general trends around this. So when we look at the things that create data, people, of course, are one of those things. There's not a tremendous amount of data sources in the world. We can go to the natural world, and observing that generates data. Human activities generates data. Machine activities generates data. And when we begin to start looking even in our last year, we start seeing a lot of human-generated data being in the, sort of high hundreds of exabytes to low zettabytes numbers. A zettabyte being a million petabytes or a billion terabytes or a trillion gigabytes, depending on how you want to think about it. A lot of this, of course, is driven by just a prevalence of networking. So I very often sort of say that our industry is a three-cylinder diesel engine where, improvements in networking drive improvements in compute, and it drives sort of a proliferation of machine and human-generated data that then leads to networking improvements and so on. So if we look at even what occurred over the number of internet users worldwide from, say, 2000 to 2010, coming into 2000, we only had 361 million people, on the internet, and then by 2010, nearly 2 billion. And out of that 2 billion, roughly half, is in Asia, and Europe coming in number 2. As we start looking at device-generated data as being something that's much more prevalent, we have lots of guys, including, say, the CTO at Intel, sort of walking around saying, as it says there, imagine a device that uses a variety of sensory modalities to determine what you're doing in an instance. And future devices will learn about who you are, how you live, work, and play. Now, the sensor-type device is exactly the thing that would be, again, collecting data about billions of people. This is then machine-generated data. Learning, of course, never happens on the device. Learning has to happen back in a data center somewhere, and then the results of that learning change what the device has done. We find ourselves actually surrounded by more and more lines of code and more microprocessors and things. Things like most automobiles have approximately 70 to 100 electronic control units inside of them nowadays. And it becomes normal to start thinking about really sort of single products, single lines of business being able to generate enough data to sort of exhaust things like the enterprise storage market. And when we begin to start thinking about even how much data, and granted, a lot of it is the same and a lot of it has the same pattern, but in terms of raw data, having, say, one 737 flight being able to generate, hundreds of terabytes of instrumentation data off of that. Now, the total sort of data demands and size of the market that's important to keep in mind, and also a good indication of the relative difference between storage that's in data centers and storage that's on devices. The enterprise storage market in 2010 was a 15.5 exabyte size market, so that's 0.01 zettabytes. The total storage device market, meaning little flash memory that goes into a watch or a phone or a remote control or something that goes in a set-top box or so on, was a 1,500 zettabyte size market. So really 99% of the storage that basically is created in a given year goes out on devices. Now when we begin to start taking that number into account as well, you can even begin to start doing iPhone and iPad math, basically, where even in terms of iPhones and iPads that were shipped in a given year, that is on the order of exabytes, in terms of distributed storage across all of those devices. And if we really sort of take, a bit more of these, into account, networks typically move about, 0.05 zettabytes per year. Compute, by most academic estimates, are actually process about 10 zettabytes a year worth of data across things that we call servers. And the entire sort of enterprise data market is only, roughly on the order of 0.01 zettabytes. And so we really sort of live in a world where, compute sees data quite a bit. Data, of course, moves and is sent and received over networks. And of course, keep in mind that besides the fact there's a lot of compute coming on, the sort of data center type numbers that you see here are really ones where, it's still only 1% of what's going on there. If we look at general sort of compute numbers, we have things like 15 billion Intel processing cores were actually shipped in 2010. We actually still have numbers like 10 billion embedded processors that were 8-bit and 16-bit were shipped in, say, 2009. And so we find ourselves even looking at embedded processors plus processing cores, and then just sort of the total number of cores and CPUs that are out there, period, right now, still being run on some type of device or in a data center. It begins to get quite a big number. I mean, if we are shipping 3 to 5 CPU cores per human being on the planet every year as a new core, you can imagine, of course, after 3, 4, 5 years of doing that, it begins to sort of add up per human being. Now, the sort of general trends per time, if we, begin to, just lay things out on an easy sort of decade basis, is, we had decentralized networking sort of show up in the mid-'70s. The PC showed up in the mid-'80s. 1985, for example, was the year that Dell started as a company. 1995, we really started doing distributed networking. 2005 or so, we actually started talking about cloud computing, meaning sort of an extension of networking concepts into the data center. And more as we head in the future, we're talking quite a bit about data. Now, the trend across all of these types of things is just that all systems over time are just going to become more distributed, right? And so when we sort of go through here and say, what is the deal with the Internet of Things? It's really around going from a centralized to a decentralized to sort of a distributed type concept. We start living in a world where, unlike, say, a centralized type airport hub, we go to a decentralized type model to a distributed type model. And so, of course, what we've done then is that exact thing over time. And we start moving from much more of, again, a client-server world to much more of a world of peers. Now, distributed is a superset, so we can actually restrict basically depending on a point in time. And distributed purely means, things are readily available and they're sort of pervasive. Now, we call most of these relatively available economic goods or commodities. Relatively available economic services are called utilities. And really, when we start thinking about, even the business of quote unquote cloud now, it's really around just the emergence of commodity and utility markets for networking, compute, and data, and really sort of living in this, the world is the computer type idea, where you actually have a world of billions of devices, things that are CPUs out there crunching and collecting data and sending and receiving it over a network or storing it locally. The data center is one big hub of that. The network basically serves as the backplane. And so when we begin to start thinking about this just as an economic reality, the bits are the economic good then. The transport of bits, bandwidth is our economic service. Latency is our service delivery time. It occurs, say, via fiber routes. It arrives at pretty much the equivalent of a port, which are data centers, and final destinations, which are devices. Now, of course, when you begin to start even breaking down both devices and servers in a data center, the bits only have a limited number of places they can live. They can live in volatile memory space. They can live in non-volatile memory space. They can actually be on a CPU and at that point have a latency measurement as well of, say, code execution latency. They can be moving over a bandwidth. That's network bandwidth, network latency. They can be moving, from memory onto a CPU. They can be coming on and off of non-volatile storage, right? And so we really have pretty much a complete list of potential commodities and utilities in this list here, right? So that being a bit. One thing to keep in mind, of course, is that, CPUs only process things that are, in memory, in RAM. And so that's exactly why that triumvirate, if you will, of volatile memory, non-volatile memory, and CPU is a pretty common thing. Now, if we're really sort of taking the port analogy and the shipping sort of route type of analogy, where we have this world that is wired, this world that has CPUs everywhere, this world that then starts behaving much more like a large computer in itself, where we have synced real-time peers, where you have data centers as being one of those, a large number of devices being the other, and we actually have to start thinking about things like, well, what's our sort of common container? Paul Baran, of course, as one of the creators of the packet switch concept, came up with the packet, as one sort of container, where one can actually look at, from Ethernet to TCP from Ethernet to IP to TCP, you begin to start having information about MAC addresses of a computer or a device, the IP address, the actual ports, and protocol types that are being used, and so on. And so when we start taking, this sort of, containers for our bits, if you will, inside this, economic model, a lot of it is saying that, well, we have a network packet, the equivalent inside computers for memory and for disk would be a compute memory block and a data object block. And so that becomes sort of our three fundamental shipping containers, in this world of things. And the interesting thing about that is that becomes the type of abstraction that we have to sort of move to, not a machine abstraction. So if we think about, the idea that we have an economic good that is a bit, the bit is carried around in a container along, service routes. It arrives at things like ports, which we can think of as a data center, or devices, which people are using on the end. A machine abstraction is not what we sort of need to deal with there to have a unified view of things. It's really around looking at things that we can actually flow, shape, time, and count. And so the data center really then, as we said, starts being thought of as a complete entity in itself, a box, a server, a peer on this Internet of Things as well. And of course, everyone, other people think this as well. I mean, for example, this is from a Google document where we say, well, we must treat the data center as one massive computer. When we start sort of thinking about that type of data generation that's coming off of user-generated data, machine-generated data off of devices where not only am I using my phone to do something like create a blog post, but the phone's actually recording where I am when I do that and what picture did I just take and so on like that. We begin to actually have quite a bit of that. And when we start even thinking about the burdens that basically places on even the abstractions that we're using for networking compute data and how they're even connected to each other, to do much of what people would like to do, it could actually exhaust things. And so we do actually have to do things like take things like RAM or just concepts there, and over the next 20 years, increase them a millionfold, right? And so, it also takes a highly decoupled asynchronous view of the world. And so, that's how the web works, that's how mobile works, that's how DNS and sort of resolution works. And both traditional supercomputing as well as, most of what we've been doing with client-server is very coupled, very synchronous, very sort of shared memory. And that doesn't reflect a world of devices. And so when we start thinking about, say, both modern data centers, it's around, understanding the actual capabilities in a data center, having it be message-oriented, just like how our communications are message-oriented. I mean, you can leave someone a Post-it note, you can leave them a voicemail, you can send them a text message. How these devices are actually being used is very much message-oriented. And what you'd sort of say naturally decoupled and asynchronous. And so we start moving towards this worldview where you have real-time data synced peers as something that's replacing client-server. So world is the computer. It's full of a bunch of real-time peers, and those real-time peers range from large computers like a data center to smaller computers like a small embedded sensor. And so when we start taking a resource view of that, the resource view is really around how do we do bandwidth around networking bandwidth, memory bandwidth, disk bandwidth. How do we have a latency premium or even control around network latency, CPU execution latency coming on and off of disk, and how do we begin to actually start abstracting these things as a space that includes, say, non-volatile, volatile memory and sort of CPU. The foundation we find ourselves building all of these things on is still, x86 for now. HTTP has been layered on top of that as a very sort of common transport protocol. The actual messaging protocol, of course, is not set in stone. Say AMQP is not by any measure one. Yet what I really see now is JSON taking off as a very common message format that you see there. And so more and more, even web applications and everything you run on a device is a web application, become these types of things where it's just one peer sending a JSON message to another peer and that one sending a JSON message back. And that's becoming a very sort of common design format. And so, our base technology view, at least at Joyent, is that, we might as well run applications very well. The data center is basically the new box, and ideally the data center runtime really sort of needs to be on devices as well. And so, that becomes in a lot of ways, what's required to head into this world. And so I think, as we're wrapping up the presentation now, it's really a couple things to keep in mind. One, when we look at actual numbers around CPUs shipped and storage shipped, what you would call, quote-unquote, enterprise CPUs and enterprise storage is really single-digit percents in terms of what is actually out there. And if you ask yourself, well, where do those things actually go? They're going into really what you would call a device. We know for a fact that half of those are at least some sort of embedded CPU that is in a more primitive device. And so we're really sort of heading into this world where there's a tremendous amount of CPUs deployed. There's a lot of little storage deployed all over the place. The network very much is having to behave as the backplane for all these interactions. And we really start thinking about the data center as sort of a back-end peer for that. And with that base concept and a couple of those facts, we can open up for some questions if anybody has any, and then call it a morning. Okay, well, it looks like there's no questions right now. So thank you, everyone, for attending. I'm Jason at Joyent.com. Feel free to reach out to me directly if you have any questions, comments, or concerns. How do you help MSPs? How does who help MSPs? Managed service providers, you mean? Oh, okay. Oh, well, I mean, yeah, okay, that's if you're thinking of Joyent as a business, how does Joyent help managed service providers have a business? Well, managed service providers historically have been doing, say, co-location and managed services around, data centers they do or do not own. And when you look at what actual sort of compute usage is, we can basically divide that between constant compute and variable compute. Okay, and so when we work with, say, managed service providers, it's really around helping them have a variable compute business, and then also a pretty complete software stack on the constant compute side that has some real benefits around performance, scalability, and sort of completely understanding what's going on. We have a pretty networking-centric view of the world, and so if you think about, very often managed service providers have a networking bandwidth business. They maybe have a latency premium involved in that, and they've been selling boxes. And so, it's for us really around, moving that into, additional types of, bandwidth, latency, and space businesses, right? Any other questions? Okay. Well, thank you very much. Take care, everyone. Bye-bye.